In this problem, we will look at a classic boom-and-strut frame. A boom-and-strut frame has a long member, usually horizontal, supported by a strut. Both of them are pinned on a wall or some other support with vertical loads. Could be on the strut as well, but in this case we'll just look at loads on the boom. In order to make a free body diagram, I must remove the supports. So might redraw it, but in this case I can just erase. And when I erase supports, get rid of supports, I have to replace them with red arrows. The red arrows represent forces that the supports provide the structure so that it stays in static equilibrium. I will not put arrowheads on here because I do not know the directions yet. So we'll label these AY and AX and EY and EX. So now I can begin my analysis. The first thing I'll do is take the moments about any point. Can take it about any point, but what we want to do is remove as many unknowns as possible. So it makes sense to take moments about either point A or point E. In this case it doesn't really matter. If you take about point A, AY and AX will both be multiplied by 0, as well as EY, because the direction of EY is going right through point A, so its direction is multiplied by 0. So we take summation of the moments about point A. They must equal 0. And let's see what we have. We're going to have P times 20 plus 30 plus 45 is 95 inches, plus Q times 20 inches. Notice how these are vertical forces. These vertical forces have lines of action that are vertical. So what we're looking for are horizontal distances to joint A. These horizontal distances again are 20 inches here and 95 inches here. Now for the other forces. AY, as we said, will be multiplied by 0 inches. AX multiplied by 0 inches. EY times 0 inches. And finally, EX times, what's the distance here? The vertical distance of that horizontal force, EX to AX, is this 45-inch distance. So we take EX times 45 inches. Finally, before we can do our calculations, we need to find our directions of our moments. P, about point A, is doing this type of motion, which is counterclockwise. So that means this moment will be positive. Okay. Q is also going the same direction. So the moment Q will be positive. EX we're going to assume is going positively. So that means it's going in this direction, which is also counterclockwise. So we assume E is positive. So P, Q, and E are all positive moments. These moments are 0, 0, 0. So we have 0 equals positive 800 pounds times 95 inches plus 1,000 pounds times 20 inches plus EX times 45 inches. If I subtract EX times 45 inches from both sides, I get negative EX times 45 inches equals $76,000 inch-pounds. That's from the 800 pounds times 95 inches plus 20,000 inch-pounds. That's from the 1,000 pounds times 20 inches. So if I add these up and divide both sides by negative 45 inches, I end up with EX equals negative 2,133 pounds. So now we know that EX is going to the left, actually. 2,1 negative 3 pounds. Okay. I can now do my summation of the moments about point E, and it's very similar to the moments about point A. AY is going to multiply by 0. EX and EY are both going to multiply by 0. AX will be a horizontal force again that we don't know, and its perpendicular distance to point E is this 45 inches. So after we do all of these calculations, A in the X direction equals positive 2,133 pounds. If I add up the forces in the X direction, they have to equal 0. And these forces are AX plus EX. There are no applied forces in the X direction. So AX is positive. We write that arrow in. 2,133 pounds. So 0 equals 2,133 pounds minus 2,133 pounds, and our check works. 0 does equal 0, and we have checked our analysis. And this is for the free body diagram of the system. Our next step is to break the system up into its component parts. This only has two parts, member AC and member BCDE. Just call it BE. So we can choose to do the easier part. AC is a strut, and for a strut, we are in luck. A strut is a member that's only loaded in two locations. If it's only loaded in those two locations, the strut is not in bending, and its force goes along the geometry in the same direction as the geometry of the strut itself. So I know that the ratio of the vertical to the horizontal is the same as the ratio of the vertical distance. So I know that the ratio of the vertical to horizontal forces is the same as the ratio of the vertical to the horizontal distances. So our slope is distance AC in the y direction over distance of AC in the x direction, and that will equal the force of AC in the y direction over the force of AC in the x direction. Usually I'll just refer to this as AC in the y, AC in the x. Luckily, this force is also equal to AY and AX. So we don't know AY, but we do know AX. AY over AX equals the distance AC in the y or the distance of AC in the x. So rearranging this equation to solve for AY, AY equals AX times the distance of AC in the y over the distance of AC in the x. Make sure we keep our minus sign straight. This strut has positive slopes, so both of them are positive or both are negative, and we'll end up canceling the two negatives out. So AX is 2,133 pounds. From A to C, we go down 45 inches. And from A to C, we go to the left, or negative 50 inches. Doing this calculation, find that AY equals 1,920 pounds. Look at member AC. We have AY here, AX here, then we have CX here, CY here. If we add up the forces in the x direction, they must equal 0. And that is AX plus CX. Solving for CX, since AX is positive 2133, CX must equal negative 2133 pounds. Likewise, adding up the forces in the y direction, they must equal 0. AY plus CY, since we determined that AY is 1,920 pounds, Then solving for cy, c must be negative 1,920 pounds. We'll just finish this off by putting the arrows on the x and y components of c. If we go back to the free body diagram of the system, we can look at the sum of the forces in the y direction. Obviously they must be 0, and we have AY plus EY. We were never able to solve them over there, but now we can. Minus P and Q, 800 pounds minus 1,000 pounds. We know that AY is 1,920 pounds. So solving for EY must be negative 120 pounds. Well, what does this mean? This means with the loads that we have here, and AY taking the load that it is, EY must actually be pushing down at point E to keep boom BCDE in balance about point C. So we'll put the arrow here and this arrow here and fill in our chart. AY is 1,920 pounds and EY is negative 120 pounds. The last thing we should do is make a free body diagram of member BCDE. In fact, we've already found all the forces on this member, so we're just going to use it as a check. We should always be checking our work. Now notice how I've made a force summary diagram up here. It should be more complete, showing the full magnitude of the forces, but for now I'm just going to put the X and Y. This will help us when filling this out for the free body diagram of BCDE. Also note, though, that joint C is an internal joint. It's not, doesn't show on the system as having any forces on it. So these values reflect the values from member AC. When we go to member BCDE, we will have to change the signs on joint C. All the other forces on BCDE are external forces that show up in the system. They're either applied, like P and Q, those are external forces, or reactions, such as the ones that support E. So here we have downward force of P, downward force of Q, EY of negative 120 pounds, and EX, which is negative 2133 pounds. And then finally at point C, we have 2133 and 1920. We have to switch the signs here. So CX, this is CY, equals 21 equals 1,920 pounds. CX equals 2,133 pounds. Now we can just add up the forces. In the x direction, they equal 0. And we have CX plus EX, and 0 equals 2,133 pounds minus 2,133 pounds. 0 equals 0. Excellent. That checks out. Now if we add up the forces in the y direction, they equal 0. We end up with CY plus EY minus 800 pounds minus 1,000 pounds. 0 equals 1,920 pounds minus 120 pounds minus the applied loads of 1,800 pounds. And this checks out as well. To complete the problem, we would find the resultant loads at joints A, C, E, and not worry about it at P and Q because they're both vertical loads. For that matter, B and D could be, it could be argued that they are the same as loads P and Q.